We have seen the quantization and overflow. That is, quantization has three forms. Okay, three common forms. First one is rounding, second one is two's complement truncation and magnitude truncation. Okay, and also you have seen the quantization noise, that is difference between the real number and the rounded off integer. Okay, that is x of n and xq of n. Now rounding. Okay, rounding. Rounding means the again the same thing, that is you are substituting the real number with the nearest integer value. Okay, that is the range can be written as minus q by 2 less than e of n, that is quantization noise, and which will be less than q by 2. Okay, which will be less than q by 2, where q will be the step size. Okay, step size. Please know these equations. Okay, and the next one is truncation. Truncation means the range can be between minus q less than or equal to e of n less than 0. This is the truncation. Okay. Now the next topic is steady state input noise power. Okay. Steady state input noise power. Steady state input noise power. In analog to digital conversion, in analog to digital conversion, x of t is given to a sampler and then quantizer. Okay, quantizer. The basic block diagram of ADC or analog to digital conversion. We can get the XQ of n. Okay, that is analog. This will be in analog nature. Okay, for analog signal sampling ചെയ്തിട്ടാണ് we will get it as x of n, and hence this x of n is quantized to get the final digital value as xq of n. And also there will be possibility of error. Okay, that is quantize ചെയ്യുമ്പോൾ അവിടെ error വരാൻ chance ഉണ്ട്. Therefore this error is again in additive in nature. Okay, in DSP the error will be additive in nature. That is x of t when given to a sampler you will get x of n. Again this will be an additive in nature. Okay, that is e of n. Finally we get it as xq of n. Okay, the error will be in additive in nature. We can represent it as an adder. Okay, and this e of n, what do you mean by e of n? The quantization noise, okay, or the quantization error. Again this e of n can be written as quantization noise or error. Okay, quantization error. This E of n, this E of n can be written as the quantization noise or the quantization error. Okay, what will be the equation for E of n? What will be the equation for E of n? നേരത്തെ എഴുതിയതല്ലേ പറഞ്ഞേ? എന്താ E of n? The difference between xq of n and x of n. Okay, E of n will be the difference between okay, the error will be in additive in nature. അതാണ് ഈ റെപ്രസെന്റ് ചെയ്തേക്കുന്നത്. Okay, and the E of n has the certain or has certain properties. Okay, that is the properties of E of n can be written as എഴുതിക്കോ. E of n is a sample sequence of stationary random process. E of n is a sample sequence of stationary random process. E of n is a sample sequence of stationary random process, and again E of n is uncorrelated with x of n, with x of n and other signals in the system. E of n is uncorrelated with x of n and other signals in the system. And error is a white noise. Okay, it is a white noise process with uniform amplitude, with uniform amplitude PDF over the range of quantization error. Okay, these are the properties of E of n. ഇതിന്റെ ഓരോ പ്രോപ്പർട്ടീസും okay. E of n is a sample sequence of stationary random process and is uncorrelated with x of n and other signals in the system. It is a white noise process with uniform amplitude PDF over the range of quantization error. Okay, ഇത് നിങ്ങൾ പഠിച്ചിരിക്കണം. Along with these properties, you have to learn the equations. Okay, equation representing these properties. Okay, we can see this one by one. Before that, again, the three properties of E of n is that the first one is that it is a sample sequence of stationary random process, and the second one is that E of n is uncorrelated with x of n and other signals in the system. Error is a white noise process with uniform amplitude PDF over the range of quantization error. Okay, so let's start with the stationary random process. Okay, now we can start with the stationary random process. Okay, stationary random process. Stationary random process. Okay. In this stationary random process, the mean value, okay, the mean value will be equivalent to the covariance. The mean value will be equivalent to the covariance, and again there will be a uncorrelation. Okay, there will be uncorrelation. Uncorrelation means there exists a non-linearity, non-linearity. Okay, and the white noise. And again the white noise. White noise means that എന്താണ് white noise ഒരു എക്സാമ്പിൾ പറഞ്ഞ white noise അതായത് all all frequency all frequency components are same അങ്ങനെ ഒരു എക്സാമ്പിൾ പറഞ്ഞ white noise ന്റെ example lightning. Okay, lightning is a example for white noise. Therefore, in stationary random process, the mean value will be equivalent to the covariance. The uncorrelation exists, that is nonlinearity exists, and the white noise. Okay, the white noise. That is the E of n is a white noise process. That means all the frequency components are same. All the frequency components are same. Again, we can write the power value of noise as power value of noise. ഇതാണ് പവറിന്റെ ഇക്വേഷൻ ഒന്ന് നോട്ട് ചെയ്തോ. This can be known as variance. Okay, this can be known as variance. Okay, this can be known as variance. The equation of variance. Okay, the equation for variance can be written as expectation of E square of n minus expectation square of E of n. ഇത് നോട്ട് ചെയ്തോ. ഇത് സ്റ്റാൻഡേർഡ് ഇക്വേഷൻ ആണ് വേരിയൻസിന്റെ. ഓക്കെ, ഇത് എഴുതാൻ ചോദിച്ചിട്ടുണ്ട്. ഇത് നോട്ട് ചെയ്തോ ഇക്വേഷൻ, എന്നിട്ട് അതൊന്ന് ഇമ്പോർട്ടൻ്റ് മാർക്ക് ചെയ്തു. Again, we can write this equation as equal to 1 by q. 1 by q, the range of minus q by 2, q by 2, e square of n dE minus 0. This will be 0. Expectation can be written as 0. This can be again after integrating and substituting the limits. We can again write this equation or value of this equation as q square by 12. q square by 12. Okay. എന്താണ് ഇവിടെ ചെയ്തത്? ഈ ലിമിറ്റ് നോക്കി, ക്യൂ ബൈ 2 മൈനസ് ക്യൂ ബൈ 2. ഇത് നിങ്ങൾ എവിടെയെങ്കിലും കണ്ടിട്ടുണ്ടോ? ഇപ്പൊ പഠിച്ചല്ലേ? ദാറ്റ് ഇസ് എവിടെ? റൗണ്ടിങ്ങിന്റെ ലിമിറ്റ് കണ്ടോ? ഇറ്റ് ഈസ് മൈനസ് ക്യൂ ബൈ 2 ലെസ് ദാൻ ഇ ഓഫ് എൻ ലെസ് ദാൻ ക്യൂ ബൈ 2. അതായത് ഇവിടെ നമ്മൾ എന്താണ് ചെയ്തത്? റൗണ്ടിങ് ആണ് ചെയ്തത്. ഓക്കെ, that is the expectation of e square of n can be rounded. Okay, that is ഇവിടെ നോട്ട് ചെയ്തോ. That is rounding. After rounding, you got the value as q square by 12. Okay, after rounding, you got the value as q square by 12. Okay, now considering the b number of bits. Now considering the b number of bits, q or step size can be again written as 2 raised to minus b. Okay, where q 2 raised to minus b ആണെങ്കിൽ we can write the variance as substituting the 2. Variance എന്താണ്? നേരത്തെ കണ്ടുപിടിച്ചത് q square by 12. Okay, By substituting the value of q as 2 raised to minus b, we can write it as 2 raised to minus 2b by 12. Okay, 2 raised to minus 2b by 12. Okay, we have seen എന്താണ് ഇവിടെ നമ്മൾ റൗണ്ടിങ് കണ്ടു സ്റ്റേഷനറി റാൻഡം പ്രോസസ്സ് കൺസിഡർ ചെയ്ത അതിൻ്റെ റൗണ്ടിങ് പ്രോസസ്സ് നമ്മളിവിടെ define ചെയ്തു and also the b number of bits we have considered the b number of bits and next we will see the truncation. Okay, next we will see the truncation. Variance can be written as again 1 by q truncation. What is the limit of truncation? എന്താണ് ലിമിറ്റ് മൈനസ് q to 0 e square of n de and again we can write it as minus q by 2 the whole square. Okay, after solving we will get it as q square by 3 minus q square by 4. That will be q square by 12. Okay, q square by 12 means the again this value 2 raised to minus 2b by 12. Okay, okay, എഴുതിക്കോ ഈ രണ്ട് കേസിലും നോയ്സ് പവർ എന്ന് പറയുന്നത് that is variance can be 2 raised to minus 2b by 12. Okay, noise power. So note ചെയ്തോ ഇത്രയും. First, we have seen the stationary random process properties. After that, we have applied the rounding, b number of bits, and the truncation. From this, we have concluded that the noise power for both the condition, okay, will be variance will be equal to 2 raised to minus 2b by 12. Now, the next topic, that is steady state output noise power. Okay, the steady state output noise power, that is x of n can be this will be the noise, this will be the h of n. Okay, h of n, and we will get the output as y of n. Okay, y of n, that is again we can represent h of n as e of n, that is noise, and h of n, and again the output will be e of n, that is where the e of n will be written as this convoluted output, that is e of n and h of n. Okay, from this the variance of output noise can be written as this will be the equation for output noise. Okay, this x square of n. ഇത്ര നിങ്ങൾ നോട്ട് ചെയ്തോ. നോട്ട് ചെയ്തോ എല്ലാവരും? ഇക്വേഷൻ ഒന്ന് പഠിച്ചു വെക്കണം. ഇത് പ്രോബബിലിറ്റിയുടെ ഇക്വേഷൻസ് ആണ് ഇതെല്ലാം. വേരിയൻസ്, നോയ്സ് പവർ, പിന്നെ ഈ റൗണ്ടിങ് ഓഫ് ചെയ്തതിൻ്റെ ഇക്വേഷൻസ്, ട്രങ്കേഷൻ, അതിൻ്റെ ലിമിറ്റ്, ആ കാര്യങ്ങളൊക്കെ നിങ്ങൾ പഠിച്ചു വെക്കുക. Next, we will move on to steady state variance. Steady state variance. We have written the variance of the noise, output noise, as variance of the output noise as equation 0 to infinity x square of n. Okay. By applying the residue theorem, we can write the variance as or this much term, okay, or this much term as 1 by 2 pi j integral h of z into h of z inverse d of z. Okay, after applying the residue theorem, you can substitute this much as this value. Okay, as this value. Okay. Now you should consider a process, that is the output signal of an analog to digital converter. The output signal of an analog to digital converter is passed through first order low pass filter with transfer function. The first order low pass filter with the transfer function h of z equal to 1 minus a into z by z minus a for 0 less than a less than 1. Okay, this will be the equation when the output signal of an analog to digital converter is passed through the first order low pass filter with transfer function h of, okay, consider this transfer function h of z as 1 minus a of a into z by z minus a. Again, we can write the expectation equation as ഇത്ര എഴുതിയെടുത്തോ? Okay. Next, we can write the variance or noise power as 1 plus 1 by 2 pi j the integral of h of z into h of z inverse the whole into z inverse dz. Okay, we can write the variance as this equation. Okay, ഇത് എഴുതിയെടുത്തു. നേരത്തെ എഴുതിയ സെയിം ഇക്വേഷൻ ആണ്, വേറെ മാറ്റമൊന്നുമില്ല. Again, what will be the transfer function when the output signal of an analog to digital converter is passed through the first order low pass filter? H of z can be written as 1 by a into z by z minus a. Okay, again, when the transfer function h of z will be equal to 1 minus a into z by z minus a, and the transfer function when z inverse is considered, the transfer function can be again written as 1 by or 1 minus a into z inverse by z inverse minus a. അല്ലേ? അതായത് ഇസഡിന്റെ സ്ഥാനത്ത് ഇസഡ് ഇൻവേഴ്സ് കൊടുത്തന്നേ ഉള്ളൂ. So we can get the transfer function h of z as 1 minus a into z by z minus a, and h of z inverse as 1 minus a z inverse by z inverse minus a. Z inverse minus a. And we can just evaluate these terms. Okay, this term we can evaluate as 1 plus 1 by 2 pi j the integral of h of z into h of z inverse dz. Okay, substituting this h of z and h of z inverse in this equation, what will you get? Substituting the h of z and h of z inverse in this equation, what will you get? 1 by 2 pi j integral 1 minus a into z by z minus a into 1 minus a into z inverse by z inverse minus a dz. Again there is a z inverse അല്ലേ? ഇതിന് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തേ ഉള്ളൂ. എച്ച് ഓഫ് ഇസഡിനും എച്ച് ഓഫ് ഇസഡ് ഇൻവേഴ്സിനും ഈ ട്രാൻസ്ഫർ ഫംഗ്ഷൻ്റെ ഈ വാല്യൂസ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തേ ഉള്ളൂ. ദാറ്റ് ഈസ് ദിസ് വൺ. Okay, so we can write it as 1 by 2 pi j the integral of 1 minus a z by z minus a into 1 minus a z inverse by z inverse minus a into z inverse into dz. Okay, then we have written this much by using the residue theorem. Okay, so we can evaluate this using residue method. How you can evaluate using residue method? That is residue at z equal to a, residue at z equal to a plus residue at z inverse equal to a. Okay, you can evaluate using residue method by taking the residue at z equal to a plus the residue at z inverse equal to a. Okay, and in this case the residue at z inverse equal to a, that is this term will be 0. This term will be 0 as this pole will be outside the unit circle. Okay, this will be outside the unit circle, and we can consider the residue at z inverse equal to a as 0 value. Okay, so there is only need for taking the residue at z equal to a. Okay, you can only take, there is only need that you should take the residue, or you should apply the residue method at z equal to a. Okay, we can apply the residue method at z equal to a, and the residue at z inverse equal to a will be considered as 0. Will be considered as 0. And and we can take the residue at z equal to a. എങ്ങനെ ചെയ്യാം? z minus a നേരത്തെ ചെയ്ത ആ ടേം z minus a into 1 minus a square z inverse by z minus a into z inverse minus a at z equal to a by applying, അതായത് എല്ലാ z-നും a substitute ചെയ്തോ. So we will get 1 minus a square a inverse by a inverse minus a. Okay, this can be again written as 1 minus a, just evaluate ചെയ്യുന്നേ ഉള്ളൂ. Okay, 1 minus a square. ഈ 1 minus a square split ചെയ്യുക, അതായത് 1 minus a the whole square by 1 minus a into 1 plus a. And you can cancel out this term and you can write it as 1 minus a by 1 plus a. Okay, 1 minus a by 1 plus a. So we have calculated the value at residue at z equal to a, and finally you can substitute in the expression for variance. You can substitute into the expression for variance, that is 1 minus a by 1 plus a, and that is variance can be written as 1 minus a by 1 plus a, and this can be again written as 2 raised to minus 2b by 12 into 1 minus a by 1 plus a. This will be the expression for variance. Okay, this will be the expression for variance. Please write this question. Derive the steady state variance. Okay, ഇങ്ങനെ ചോദിച്ചു കഴിഞ്ഞാൽ ഇത്ര എഴുതിയാൽ മതി. ഇത്രയും ഒരു എക്സ്പ്രഷൻ, ലാസ്റ്റ് വേരിയൻസിന്റെ എക്സ്പ്രഷൻ ഇങ്ങനെ കിട്ടുന്ന വരെ, അതാണ് ചോദിച്ചിട്ടുണ്ട് യൂണിവേഴ്സിറ്റിക്ക് ഈ ഒരു ഡെറിവേഷൻ. ഓക്കെ, റെസിഡ്യൂ മെത്തേഡ് യൂസ് ചെയ്തിട്ട് നിങ്ങൾ ഡിറൈവ് ചെയ്താൽ മതി ഈ ഡെറിവേഷൻ, അതായത് സ്റ്റഡി സ്റ്റേറ്റ് വേരിയൻസിന്റെ. ഓക്കെ, എഴുതിയെടുത്തോ ഇത്രയും? എഴുതിയെടുത്തോ? So we have seen the steady state variance expression or the expression for variance. ഓക്കെ, ഇത് തൊട്ട് നിങ്ങൾ എഴുതണം. സ്റ്റഡി സ്റ്റേറ്റ് വേരിയൻസ്, അതായത് വേരിയൻസിന്റെ എക്സ്പ്രഷൻ, അതിൽ നിങ്ങൾ റെസിഡ്യൂ തിയറം അപ്ലൈ ചെയ്തിട്ട് you have written the condition that when the output signal of an converter is passed through the first order low pass filter, and again you have substituted the transfer function expression, that is h of z and h of z inverse, and you have evaluated this by using the residue method. Okay, by using the residue method, and for that you have applied the residue at z equal to 0, and you have taken the value and substituted the residue value at the earlier variance expression. Okay, ഈ എക്സ്പ്രഷനിൽ നിങ്ങൾ എന്ത് ചെയ്തു, ഇത് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തു. So that you got the value as 2 raised to minus 2b by 12 into 1 minus a by 1 plus a. This is an important question, and it is asked as derive the steady state variance. Okay, derive the steady state variance. Next topic is the product quantization error. Okay, the product quantization error. Product quantization error. Product of 2b bit എന്തായിരിക്കും? അതായത് 2 ബി ബിറ്റ് ഉള്ള നമ്പറിന്റെ പ്രോഡക്റ്റ് എടുക്കുമ്പം usually they consist of, or the product consists of 2b number of bits. Okay, 2b number of bits. Here also the error will be additive in nature. Okay, that is xq of n a plus y of n. You can represent it as this. Okay, additive in nature, where y of n will be equal to a into xq of n plus e of n. Okay, y of n can be represented as a into xq of n plus e of n. Okay, that is each multiplier is replaced by an multiplier and an add-on. Okay, this will be the expression for product quantization error. Okay,